Okay, this is going to be our first video on inductance. So this is chapter 30 from the text. We're going to be doing about four of the sections from this chapter, and this is going to be our last module. But we're also going to be doing a couple of sections from the last chapter on electricity and magnetism in the textbook, which is chapter 32. So we're going to do a few sections from chapter 30, so it'll be like 30.1, point 2, point 3, and point 4, and then we're going to do the first two sections of chapter 32, skipping over the last sections of chapter 30 and all of chapter 31. Okay, so this video is going to deal with mutual inductance, and all the material covered here corresponds to section 30.1 from the text. And so I guess I'll get started here, and we'll see how the rest of the module works itself out with the sort of two combined chapters worked into one module here. Okay, so we've seen, or maybe we haven't seen yet, but we will be seeing, how a change in current in one coil, let's say we have two coils, a change in current in one coil is going to induce an EMF in another coil. This is very similar to what we saw where we had a current running down a wire inducing a current or an EMF in a nearby coil. Right now we're going to be dealing with two coils. We're going to see that the change in current in one coil induces an EMF in another coil, and that the coupling between the two coils is described by their mutual inductance. Okay, so we're gonna talk about mutual inductance. This is the topic of this video. This is one of the topics we're going to be discussing in the chapter. We're also going to discuss in this chapter how the change in current in a coil also is going to induce an EMF in that same coil. Okay, and that's going to be called inductance or self-inductance. That's going to be the topic of our next video. And in this chapter, we're also going to talk about the energy stored in magnetic fields. This is the so-called magnetic field energy, and that'll be the topic of likely our third video. Okay, so we'll get to those in a bit, but for now, we're going to be focused on mutual inductance. That's the topic of section 30.1 from the text, and so let's get into it here. In section 28.4, we looked at how the magnetic interaction between two wires that are carrying steady current sort of works, right? So we saw that if one wire is carrying current, it produces a magnetic field. This magnetic field exerts a force on the other current carrying wire, or the other chunk of current, right? There is another interaction which arises when we have, between two currents, when we have the current changing. So in the first case, we had the wires carrying steady current, okay? But if we have a changing current in the wires, we're going to see how this can lead to other considerations that we need to take a look at, okay? So what we're going to do now is we're going to consider two coils. We're going to consider two coils of wire that are sort of close to each other, and we can kind of look at the situation that we have here. So let's imagine that this here is coil 1. We can imagine it like this. We have current running around it in this direction, so it would be going around the loop like this, producing a magnetic field around the coil that kind of looks like these blue lines here, right? So this B is the magnetic field produced by coil 1, and we have coil 2 also sitting here in the magnetic field of coil 1. And we can see that because we have these magnetic field lines going through coil 2, well, there is in fact going to be a magnetic flux through coil 2, right? And coil 1 will have N1 turns, and coil 2 will have N2 turns, okay? And so, well, maybe I'll scroll down to the rest of the discussion here. So we can see that we have I1 here flowing through our first coil. This is producing what I've said was B, right? And so we've labeled the flux going through our loop 2 here, or our coil 2, as the magnetic flux 2. Okay. And so if we have I1 changing, and let's remember we're labeling these I's with lowercase because they're quantities which we expect to be changing in time. So if we have I1 changing, then clearly we have a changing flux through coil 2, right? If I1 is changing, then our phi B2 is changing, okay? In this case, we know that Faraday's law says that we have an EMF induced in coil 2, right? And so we have this changing current in one that is inducing a current in the second one, right? Because this EMF is going to drive a current in our second coil, right? So let's take a second and think about what's happening here. So we have current going through coil 1. It's producing a magnetic field, but if we have a change in current, well, then we have a changing magnetic field. If the magnetic field is changing, then the magnetic flux going through 2 is changing. If the flux going through 2 is changing, Faraday tells us there is an induced EMF in 2. And if there's an induced EMF in 2, we have a current in 2. So a changing current in 1 produces current in 2. Okay? Okay, so that's the sort of situation that we have here. Again, I make a note that we're using these lowercase i's to represent currents that are changing in time. We know that we can write down the induced EMF in coil 2 using Faraday, as we see here. If we take our change in, well, our timed rate of change in our magnetic flux going through the second coil to be phi B2, then n times phi B2 is actually the full amount of well, we're just basically multiplying by the number of turns in our coil, right? So we need to take that N2 into account. So this is really the expression for the induced EMF in the second coil, okay? Now, this magnetic flux through coil 2 is proportional to our current 1, right? We just talked about how these are all connected variables, right? These all relate to each other in some way. So if I1 is changing, well, then phi B2 is changing, okay? And if this is true, then it's certainly true that phi B2 times N2 times the number of turns in our second coil is also proportional to our current going through the first coil, right? Has to be, right? Because N2 is a constant, okay? And so if this is the case, this means that we can write our number of turns in coil 2 times the magnetic flux through coil 2 as some constant of proportionality times our I1, okay? So this is exactly what this is. This M21 is really just a constant of proportionality, which we call the mutual inductance, okay? So that's just this constant that's going to give us the relationship between I1 and N2 times phi B2, okay? So let's keep in mind here, again, that phi B2 is the flux through a single turn of the coil. So we do need to multiply here by N2 for this to make sense, okay? If we then use this expression that we just built up here and go back to our equation 1 here and simply replace our N phi B2 by M21 I1, then our time derivative is only going to hit on the current. Only the current is changing in time. This constant proportionality is a constant. It's not going to be changing. And so this is true too, okay? So we can solve for our EMF in the second loop in terms of this mutual inductance, this constant proportionality, times the time derivative of the current in the first coil, okay? And we can also take this expression here, expression number 2, and solve for M21 if we want, okay? We can solve for our mutual inductance in terms of these variables here. All right, so when we're in a vacuum, this M21 really is a constant, and we only deal with vacuums in this course, so we're always going to be talking about, in a vacuum or basically something that very closely approximates a vacuum, like the air at ground level here, basically is a pretty good approximation for a vacuum for these types of calculations. Okay, so this constant, this M21, depends. Well, when we're in a vacuum, this constant M21 depends only on the sort of geometric qualities of our setup here. So it's only going to depend on the size of our coils, the shape of our coils, the number of turns in the coils, and how the coils are oriented with respect to one another, right? Like, are they directly lined up? Are they somehow off kilter? Are they oriented in different directions? Whatever. But if you have those values fixed, then M21 is a constant, okay? And it is a constant that you could figure out if you knew all these other geometric factors, okay? If we now repeat the same procedure that we just went through to sort of figure out what the induced EMF in coil 2 is, if we go through that same procedure again, but we just flip the roles of coil 2 and coil 1, so now we're passing a current through coil 2, and we're taking a look at what kind of current is induced in coil 1. We can go through that whole same argument, and in that case we would be looking for M12, right? We were looking for M21 here, but in this new case we'll be looking for M12, okay? But it turns out that if the geometry of the situation stays the same, if we still have the same coils oriented in the same way and nothing else has changed, then it's always true that M12 is equal to M21, okay? And since these are always equal, M12 and M21, in the case where nothing else changes, where we still have the same setup, since they're always equal, we just drop the subscripts and we just call these M. So M is going to be our mutual inductance, and in that case, I think I have it here, yeah. So in that case, we can write, looking at this equation here, we can write M either in terms of the number of turns in coil 2 times the magnetic flux going through coil 2 divided by the current in 1, or we can just flip the 1's and the 2's, and we can write it in terms of the number of coils, or the number of turns in coil 1 times the magnetic flux through coil 1 divided by the current in coil 2, right? So just flipping which coil is which in the setup. Both results will be the same if the geometry stays the same and if we're in a vacuum not close to any large, strong, permanent magnets, right? And so this is our mutual inductance of coils 1 and 2, right? And from what we said above, we can also write our induced EMF in both of these forms, right? This is just this equation 30.4 here. This is just a sort of rehashing of number 3 here, equation 3 that we discussed a moment ago, right? So we can write it for induced EMF 2, like the induced EMF in coil 2, or the induced EMF in coil 1. All right. So we have these new equations. I should mention that the SI units of mutual inductance is called, well, they're called henries for historical reasons, and 1 henry is 1 Weber per amp. Okay. So I make a note here at the bottom of the notes that mutual inductance can be sort of a nuisance when you're working with electric circuits. Like in some cases, you're going to have changing current in one section of your circuit, and you don't necessarily want it to induce an EMF in another part of your circuit, some other circuit element you have nearby. So it can cause issues, right? You need to be aware of these things if you're dealing with sufficiently large changes in currents that you're going to get induced EMFs that could cause problems for your circuit, right? So in some cases it can be a little bit of a hassle. But in other cases, it's exactly what you want. Like transformers, when you're dealing with alternating current, work for exactly the reason that this stuff happens, right? So I won't go into the sort of engineering side of things here, but if you're thinking about currents running through circuits, you should always kind of be thinking, well, is this going to induce an EMF in another nearby circuit? Could this be a problem, right? So stuff to consider if you're working with large networks where you could run into problems. So sort of back to the more sort of fundamental questions here. We're going to take a look at a couple of examples. In this first example, we're going to calculate the mutual inductance for this set of coils. So let's start off with that. Okay, so in one form of a Tesla coil, so we go into the question here that a Tesla coil is just a high voltage generator popular in science museums. We have a Tesla coil in the lab. I don't think you guys have a chance to see it this year, and probably with the present situation, they would be a little more careful about having people group up, right? So you probably won't see a demonstration of the Tesla coil, but I think we still have a working Tesla coil in the lab. In any case, it's not really important. All we need to know for this question is that a Tesla coil generates this sort of high voltage, and it's kind of made up of this setup that we see down here. At least some of them are made up of the setup that we see down here. Okay, so the setup that we're talking about here is a long solenoid with length L. We can see it here. This is our long solenoid with length L, and a cross-sectional area A. We can see that. So this is our cross-sectional area here, and it's closely wound with N1 turns, right? So there's N1 turns in the golden-looking coil here, and we have a second coil with N2 turns. We can see it made out of the silver wire here. Excuse me. And the second coil surrounds our first coil. Okay, so we want to find the mutual inductance M of these two coils. Okay, in this setup, right? And this mutual inductance M, this is going to be the inductance for this coil or these two coils for as long as their geometric properties remain the same, right? If I go ahead and undo, if I take off some of the coils here, like if I remove some of the number of coils, or if I pull the silver coil away so it's no longer surrounding the golden coil, obviously M doesn't apply to that situation anymore. It only applies where we have the same geometric properties as when we calculated it, right? And calculating it is exactly what we are going to do here. Okay. So I think I have some numbers here. Okay, well we're not given numbers in the statement of the problem here, but we do add some numbers to it afterwards. So we're going to get those numbers and then move forward into another problem with those numbers. Okay, so we definitely have mutual inductance here because if we run current through either of these, we definitely have magnetic field being changed, right? We have magnetic field being produced, and that magnetic field runs through the other coil, right? So we definitely have magnetic flux through whichever coil if one of them is having current run through it, right? And from our earlier work, we know that the magnetic field at the center of a solenoid, let's say at the center of coil 1 here, our thing with N1 turns, is going to be equal to B. At least the magnitude of this magnetic field is going to be equal to B is equal to mu naught Ni, and I guess I could write that with subscript. So we could write that the magnetic field produced by 1, which is our solenoid here, is equal to mu naught times N1 times I1. That's the current running through our solenoid. But we have to remember that N1 here, this is a measure of the number of turns per unit length. So N1 is really equal to N1, like capital N1, the way it's said in the problem here, over our length L. Okay, and so we can rewrite our magnetic field here as B1 is equal to mu naught N1 I1 over L. Okay, so that's our magnetic field inside of our sort of golden looking solenoid here. Okay. So the flux through a cross section of our solenoid, we could do the sort of whole integral writing down what flux is, but we've done this many times. So we know that the flux through this circular cross section of our solenoid is simply going to end up being B1 times the cross sectional area, right? This is the B1 that we just calculated. So I can rewrite this. I can substitute in the value for B1 here, and we're going to end up with a mu naught N1 I1 A over L. Okay, and that is our magnetic flux through this solenoid. But it's also the magnetic flux through this solenoid, right? Because of the way they're lined up, both solenoids end up having the same magnetic flux running through them for now, right? If we're passing current through this solenoid, it sets up a magnetic field inside it, and inside this solenoid is also inside of this coil, right? And so we can call this magnetic flux through B2, through 2, right? So I've changed the label here if you guys didn't notice. This is the flux, the magnetic flux through coil 2. All right, so we can then ask ourselves, well, what what is the mutual inductance here, right? We have an expression now for mutual inductance right here. We know what the flux through B2 is, or through 2 I should say, is the magnetic flux through 2 is. We know the number of turns in coil 2, and we know what or at least in principle we would know what the current we're running through I1 is. So we can kind of write it down like this. We can write just from that expression above, we can write our mutual inductance is N2 times the magnetic flux through 2 over I1. Okay, and I'm just going to substitute in for the magnetic flux here, so we're going to end up with N2 over I1, should probably make that a smaller one, times mu naught N1 I1 A over L, right? These I1s are going to cancel, and we're going to end up with an expression for our mutual inductance being equal to mu naught A N1 N2 over L. Okay. Now, I should point out one thing, that when we're doing this calculation of the magnetic flux, this is really the average magnetic flux, right? Because we know that, I guess in the case of going in this direction, it's not that bad. But let's say we were calculating the magnetic flux running through the solenoid due to the magnetic field of our second coil. Well, the magnetic field of the second coil kind of goes like this, right? Like it runs through here, but it kind of starts to curve. So this is the average. This is the average over all of these different turns of the solenoid. Okay, so the magnetic flux is not exactly that value, probably almost anywhere. It's more the average through this thing, right? But we don't have to worry about that too much. We are looking for the average, and this is the value that we end up getting, sort of jumping back to our mutual inductance. This is the value that we end up getting. We're going to use this result in the next problem, so I'm going to put some numbers to it so we can actually carry it forward. Let's say that we have an L, like a length for our solenoid, of 1/2 meter. Let's say that we have a cross-sectional area for the solenoid of 10 to the minus 3 meters squared. Okay, so it's kind of a long, thin solenoid. Let's say we have 1,000 turns in our solenoid. And let's say that we have 10 turns in our coil that surrounds the solenoid, this sort of silvery looking thing, right? So 10 turns in silver, 1,000 turns in the gold thing. If we take all these numbers and substitute them in over here, we're going to find that we have a mutual inductance equal to 25 times 10 to the minus 6 H. Okay, and so H again for henries, right? And so this is kind of a fairly typical number that you might run into like this. The solenoid's pretty long, 1/2 meter, but it's not ridiculously long. You could run into a solenoid of that length. There certainly are many of them out there in many applications in the real world. The cross-sectional area makes sense also. It's not overly huge or overly tiny. 1,000 turns is reasonable, and 10 turns is also reasonable for your secondary coil. So this is a fairly reasonable number that you might run into depending on the calculations you're doing, right? So let's take that number forward. It's going to be our mutual inductance that we're going to use in the next problem when we get to actually needing to run some numbers. Okay, in the second problem here, we're looking at the EMF due to mutual inductance. Okay, so we're looking at the previous problem, but we're changing some stuff. So let's say, well, let me just read the problem here, I guess. In example 30.1, which is the one we just did, suppose that the current I2 in the outer coil is given by this expression here. So I2 as a function of time, right? Note that we do have a t here, so this thing is changing in time. They could have written this as I2 as a function of time is equal to this, right? Because there is a t in it. And so this thing is changing quite quickly. The problem goes to the trouble of telling us that it is possible for currents to change this quickly over brief time periods. So that's fine. And in part A, we want to know at time t equals 3 times 10 to the minus 6 seconds, what is the average magnetic flux through each of the solenoid through each turn of the solenoid, right? And this kind of leads back to what I was talking about before, that we're really talking about average flux when we're talking about these solenoids that have some extent to them, right? Because the magnetic fields are not exactly perfect, but average flux is often good enough. And the question asks us for average flux, so let's find that average flux, okay? So in part A, we have a time equal to 3 times 10 to the minus 6 seconds. And we want to know what I2 is at that time. We know that I2 is a function of time, so this is just going to end up being 2 times 10 to the 6, and then we're going to multiply this by t, which is 3 times 10 to the minus 6. Well, we can see what's going to happen here. These are going to cancel very quickly, and we're going to find an I2 of 6 amps. Okay, so we just found what the current was at that time, but the current's not exactly what we're looking for, right? We're looking for the average magnetic flux at that time. How can we solve for that? Well, we simply go back to the expressions that we developed at the end of the sort of at the end of this section here, and we can see that we have an expression that relates our magnetic flux to to the number of turns, to our current, and to our mutual inductance. We have a mutual inductance that we came up with in the previous problem, so we can actually sort of tackle this, right? So just using equation 30.5, we can write M is equal to N1 times magnetic flux 1 over current 2. We just calculated, well, okay, I mean, first let me reorganize this. What we want is the magnetic flux in the average magnetic flux going through each turn of coil 1. This is going to be equal to M over I2, or MI2 over N1, sorry. And now we can just sub in the values for these, right? We can see right away that we can use our M from above, so that'll be 25 times 10 to the 6, or it was minus 6, right? And then we have our current. We just calculated that was 6 amps. And then the number of turns in coil 1, well, that's 1,000 turns, right? If you do the calculation, you're going to find that the magnetic flux, or the average magnetic flux through each turn of coil 1, is going to end up being 1.5 times 10 to the minus 7 Webers. Okay, and that is the answer for part A here. In part B, we want to know what is the induced EMF in the solenoid, right? Well, we can find that pretty quickly from the equations that we generated above also. This is our induced EMF. We want the induced EMF in coil 1. So, I mean, it really doesn't matter. You just have to change the numbers around. But we'll use this expression here. So the induced EMF in coil 1 is going to be equal to the negative of our M here times the time derivative of the current 2. Okay. So basically, let me just rewrite that here. We're going to have induced EMF in 1 is equal to negative M di2 by dt. Okay, and we can right away go to numbers here. This is going to be equal to minus, well, our 25 times 10 to the minus 6, and then d by dt of simply our I2 current, right? Well, our I2 current does vary in time, so we can take its time derivative, right? And that's going to be 2 times 10 to the 6. So we have a 2 times 10 to the 6 t, right? This time derivative only hits on the t, so these basically go away, right? We take the derivative of t with respect to t, we just get 1 back, and we just have to do this multiplication. This 10 to the power of 6 cancels this 10 to the power of minus 6, and we simply end up with minus 50 volts, okay? So we get an induced EMF of minus 50 volts in our solenoid if we run the setup this way, okay? And so that's going to be it for this section, yeah, I guess I won't say anything else about the section. We'll see how about the chapter. We'll see how the whole thing plays out, and I'll see you guys in the next one.